something really fast. All right. So this is on? Okay, cool. So this is Scott Denton, aka Scott David Denton, or Thor, Thorr in the future, or the TH is silent. And then Brad Golombowski here is who inspired me because he's like, we gotta make gold. I'm like, yeah, I gotta figure it out. So we did figure it out. All we have to do is pretty easy. Look, I'll AI explain it. All right. Let's just have AI explain it because like it's like it kind of seems really easy in my mind now that I did it, but like. All right, now she's going to explain how we can make gold easily with just a spinning thing and mercury, which is easy to find.
One, target selection, isotope enrichment, natural mercury. Natural mercury is composed of several isotopes. We need to enrich the sample to increase the abundance of MErCuRy 196 to the power of 9 to the power of 6 Hg, the optimal isotope for this transmutation. Isotope separation. Methods for isotope enrichment include gas centrifugation. Utilizes the slight mass difference between isotopes to separate them. Heavier isotopes tend to concentrate near the outer wall of a rapidly spinning centrifuge. Laser isotope separation. Employs lasers tuned to specific frequencies that interact differently with different isotopes. This can selectively ionize or excite specific isotopes, allowing for their separation. 2. Neutron source. Particle accelerator, cyclotron, principle. A cyclotron accelerates charged particles, protons or deuterons, in a spiral path using a magnetic field. Key components. 2 D-shaped electrodes, Ds. These electrodes are placed within a strong magnetic field, alternating voltage. An alternating voltage is applied between the Ds, accelerating the particles each time they pass through the gap. Particle motion. Magnetic force. The magnetic field forces the charged particles to move in a circular path. Centripetal force. This force is provided by the magnetic field, F_magnetic equals
Exactly.
QV,
Just don't get too
B,
close to it,
where
it'll kill you.
F_magnetic is the magnetic force, Q is the charge of the particle,
And
V is the velocity of the particle, B is the magnetic field strength, centripetal acceleration, A_C equals V²/R, where A_C is the centripetal acceleration, is the radius of the circular path, cyclotron frequency. The frequency at which the particles circulate within the cyclotron is constant and given by F equals Q, B, so 2 pi m, where F is the cyclotron frequency, m is the mass of the particle. 3. Neutron production. Nuclear reactions. Protons or deuterons accelerated by the cyclotron are directed at a target material, e.g., beryllium, deuterium.
I've never even heard of deuterons.
Beryllium target. H plus to the power of 9.
Oh,
B right pointing arrow. B aims right pointing arrow.
No,
B plus
you don't
N,
want to do any
where
beryllium.
H is a proton. To the power of 9B is beryllium 9. B times is an excited state of beryllium 10. B is boron 10. N is a neutron. 4. Neutron capture and transmutation, interaction.
Well, beryllium is
Neutrons from the target interact with to the power of 9 to the power of 6 Hg nuclei. Neutron capture to the power of 9 to the power of 6 Hg ne plus N right pointing arrow to the power of 9 to the power of 7 Hg. Beta decay to the power of 9 to the power of 7 Hg undergoes beta decay. To the power of 9 to the power of 7 Hg right pointing arrow to the power of 9 to the power of 7 Au plus E plus N where E is an electron beta particle. Neutron to the beta power of 9 to the power of 7 Hg nu. 5. Gold separation and recovery. Chemical separation. The irradiated mercury sample is chemically processed to separate the newly formed gold from the remaining mercury and other reaction products. Purification. The extracted gold may require further purification steps to achieve high purity. Mathematical considerations. Neutron capture cross-section. The probability of a neutron being captured by a to the power of 9 to the power of 6 Hg nucleus is described by the neutron capture cross-section, sigma. This value is specific to the isotope and neutron energy. Reaction rate. The rate of the neutron capture reaction is proportional to the neutron flux, phi, and the cross-section rate equals phi sigma n, where n is the number of to the power of 9 to the power of 6 Hg nuclei. Yield calculation. The yield of gold produced can be estimated based on the neutron flux, irradiation time, cross-section, and the initial amount of cross-section to the power of 9 to the power of 6 Hg. Simulation. Computer simulations using computational methods, e.g., Monte Carlo methods, can be used to model the particle trajectories within the cyclotron, predict neutron yields, and optimize the experimental setup. Important notes. Efficiency. This process is extremely inefficient. The majority of mercury atoms will not undergo transmutation. Radioactive waste. The process generates significant amounts of radioactive waste that requires careful handling and disposal. Cost. The energy costs associated with operating the cyclotron and the costs of isotope enrichment and chemical...
Let's make the process better. Well, we did do it. We figured it out. It's just very inefficient, so we have to figure out how to make this process better. So we'll call this alpha tests. How to make gold. How alpha 1. It's not even in beta testing, but there it is.